Dear student, the last topic of the colligative properties in the solution unit. In generally, the colligation properties or colligative properties, the solution which depends only on the number of the particle of solute. Okay, there is a solution that is only depends on the number of particle of solute. That is for colligative properties. So they have the colligative properties in four types. There is a types that is equal to four types. What are that four types? In the case of first one, there is a relative lowering of vapor pressure, and the second case, there is an elevation of boiling point, there is a delta TB, and the third one, there is a freezing depression of freezing point, there is a delta T of FA, and there is fourth one, there is for osmotic pressure, there is a osmotic pressure. Okay, so such a four kind of that the types in the colligative properties covered in the NCERT book in as well as the Neet syllabus. Okay, first of all, the colligative properties are directly proportional to there's a concentration. Okay, so then colligative properties are directly proportional to number of the particles, and or there's a number of molecules. Okay, or there's a number of ions. Okay, so and number of moles of solute and mole fractions of solute, such like that. The colligative properties are directly proportional to for that in generally in the case of concentration. Okay. Okay, now see the first type, that's a relative lowering of vapor pressure. That is nothing but the differences between the vapor pressure of a pure solvent and vapor pressure of there is a solution, pure solvent and solution. That's vapor pressure of pure solvent and the vapor pressure of solution. Such a differences that's called for the vapor relative lowering of vapor pressure. Okay, in generally, see there is a in case of the pure solvent, if only at the surface of that liquid is containing in the case of pure solvent. Okay, so then here the creating the vapor pressure, it's depends on that the pure solvent. It depends on that the pure solvent. If you assume the solution, such solution means that containing the solute as well as a solvent. This for the solution is for the pure solvent. Okay, that's for the pure solvent. In the case of a surface of this solution, both solute as well as a solvent are presented. Here, if you assume as a solute or non-volatile, for in the case of vapor pressure is only depends on that the solvent. Okay, because the solute or non-volatile solute, for that reason the vapor pressure only depends on that the solvent. Okay, because the solute or the non-volatile. If you assume this solvent as well as a solution relation in the case of according to Rowler's law, that is a pressure of solution is equal to P naught and mole fraction of the solvent. Okay, because in the case of solvent only we have taken here because of the solute or the non-volatile. Okay, for that reason the vapor pressure only depends on the only depends on that the solvent. The next, we know that in the case of mole fraction of the solution is equal to 1. So such solution means containing solute and solvent. For that reason, mole fraction of the solute plus a mole fraction of the solvent is equal to 1. Okay, if you need to the mole fraction of solvent, we can go to rearrange for this equation. So there is a mole fraction of the solvent that is equal to 1 minus a mole fraction of the solute. Okay, mole fraction of solute. So we can go to substitute in this equation from there is a mole fraction of or partial pressure of solution divided by P naught is equal to there is a mole fraction of there is a solvent. So we come to substitute here. There is a mole fraction of solvent to this value. What did happen? There is a P of S divided by P naught is equal to 1 minus a mole fraction of the solute. Okay. So this is like that. It will come in this formula. So the mole fraction of solute we need. The mole fraction of solute. What happened? The mole fraction of the solute that is equal to equal to P naught minus a P of S divided by there is a P naught. This formula is the most important for the relative lowering of vapor pressure. Okay. Now the mole fraction is regarding the number of moles relating. So there is a P naught minus P of S is equal to delta P. So therefore, there's a X of solute is equal to delta P divided by there's a P naught. So now we can rearrange this formula. There's a P naught delta P divided by P naught is equal to there's a X of the solute divided by X of the solvent, and also that there is a delta P divided by P naught or PS. Okay, there's a PS that is equal to weight of the solute divided by weight of the mass of there is a given weight divided by molecular weight of that solute into there is a M of the solvent divided by weight of the solvent. This formula also is the most important. Okay. Then next we go to that the elevation of boiling point. That's a delta TB. Okay, so here the elevation of boiling point is nothing but non-volatile solute is dissolved in a pure solvent. Okay, there the difference between the pure solvent and as well as a solution. So there is a elevation of a boiling point. Elevation of boiling point that is equal to that is nothing but delta TB. That is equal to there is a TB minus a T naught. Okay, so there is a TB naught. So in generally, see this graph between the vapor pressure and there is a temperature. So there is a barrier of the atmospheric pressure. Here there is a 1 atmospheric pressure. If we cross this solvent, so that is after this point that will become to the vapor. And this is the solution. Okay, this for the solution. In generally, the solvent it is a low temperature and compared to the solution. There is a T naught. This for the TS. Okay, the solution of a boiling vapor pressure point there is a greater compared to the solvent. For that reason, there is a delta TB is equal to TB minus TB naught. Okay, this formula will come. Okay, so in generally there is a elevation of a boiling point that's directly proportional of the molality. Okay, so there is a delta TB is directly proportional of molality. We know that molality formula as well as we can introducing the proportionality constant here. There is a delta TB is equal to Kb into small m. Okay, so now the Kb is nothing but that is for the molar elevation constant or ebullioscopic constant. Okay, there is a ebullioscopic constant. There is nothing but ebullioscopic constant. Okay, so and also we studied already that molarity topic. This molarity is equal to given weight divided by molecular weight into there is a 1000 divided by weight in gram for that solvent. Okay, so this formula we can go to introducing the this molarity formula into here. There is a rearranged formula. Another one is we will get it. Okay, so then the delta TB that is equal to there is a 1000 into Kb into small w and m into w. Okay, so this is a formula. If you needed for this value, there is a m is equal to 1000 into Kb into w divided by delta TB into w. Okay, so this is a formula. So there is a most easy topic. This formula is most enough for the calculation. Okay, now let's see the third kind of colligative properties, such as the depression of freezing point in the solution. There, the graph they have given in the vapor pressure as well as the temperature relation, vapor pressure and the temperature. Okay, so now see the graph is like that is happened, and this like that. This point it is for that, and also this point is for that. They have conversion of one phase to another phase. Okay, so this for the T naught of F for pure solvent. This for the TF for the pure solution. Okay, the solution means they have containing the solute and the solvent. Here, this temperature is lesser and compared to this temperature is highest. So therefore, the delta TF that is equal to there is a TF naught or T naught F minus a TF for this formula will come. And also this the depression of freezing point also is direct of the molarity, directly proportional molarity. So delta TF is directly proportional molarity. So we can introducing a constant such as there is a delta TF is equal to KF molarity. Okay. So now we can say this KF is nothing but such as there is a molar depression constant or cryoscopic constant. It's a cryoscopic constant. Okay, this is a cryoscopic constant, and this formula is a delta TF is equal to there's a 1000 into KF into W divided by there's a molarity into weight. If you needed for that molarity, that's equal to 1000 into KF into W divided by delta TF into W. Okay, this formula is the most enough for calculation in the Neet and JEE problem. Now see the last colligative properties. There is a osmotic pressure that is representing the pi. Okay, so in generally we know that osmosis and reverse osmosis as well as osmosis and diffusion differences and applications of osmosis like that. Now if you assume when the osmosis is occurred and when the reverse osmosis occurred and when is not at all possible reverse osmosis as well as osmosis. In generally the solvent molecules are move lower concentration to higher concentration. Okay, that is for the through the semi-permeable membrane. That is for nothing but for the osmosis. The reverse phenomena that is for the reverse osmosis. If you note this important point, there's a external pressure that is equal to osmotic pressure. There's a no process. Okay, no process is happened. If the pressure of external that's a greater compared to the osmotic pressure, that is for occurred in the reverse osmosis. Okay, and there is a pressure of external that is less than the osmotic pressure, that is equal to occurred in the osmosis process. Okay, that's occurred in the osmosis process. This is sometimes asking the question in the simple way. Okay, if they are asking the simple question, that is happened. Okay, then according to the Boyle-Vanderhoff law, they have the pi is directly proportional of concentration, and according to the Gauss-Lussac law, there is this nothing but there is a the concentration is directly proportional to osmotic pressure, such as the obeying the Boyle's law. Now see the Gauss-Lussac law. There is a pi is directly proportional of temperature. We can go to relating these two formula, 1 and 2, this 1 and second formula, that's a pi is directly proportional of Ct. Okay, so now we can go to introducing the constant such as that is a proportionality constant. So now that's a pi is equal to C or T. Okay, so this R is a constant, this is a constant. So okay, so first of all, the concentration, what we know, concentration is equal to number of moles in particular volume. We can go to introduce here, that's a pi is equal to N by V or T. Okay, so now this V is rearranged here. What happened, that's a V pi is equal to N or T. Just to remember, this formula is similar like that, that's a PV is equal to N or T formula. That is nothing but for the ideal gas formula. Okay, ideal gas formula, this okay, that is PV is equal to N or T. Okay, now the pi is equal to this formula is very important. Notice pi is equal to, that is a W divided by weight, this is given weight divided by molecular weight into RT divided by volume. So this one of the formula is very important. That's the most important for calculating this osmotic pressure regarding colligative properties subtopic. Okay, dear student, finally we are relating the osmotic pressure into the various colligative properties. Okay, so there are three formulas there. First case, there is a relative lowering of vapor pressure. There is osmotic pressure versus the relative lowering of vapor pressure. We can go to relate this formula. That's a pi is equal to P naught of A minus A. That's a P of A divided by, that's a P naught of A into D or T divided by M. Okay, this formula is the most important. And the osmotic pressure versus or elevation of a boiling point, that is a delta TB. So that's such a relation. That's a pi is equal to delta TB into, that's a DRT divided by 1000 into KB. So it's such a formula is the most important. And the last one case, there is a osmotic pressure pi and there is a elevation of boiling, depression of freezing point, that's a delta TF. So here pi is equal to delta TF into the DRT divided by 1000 into KF. So those three formula is the most important. Actually the content they have a very large, we need to most important formulas like that I given in this video. And similarly, the two solution, if you assume one is a higher concentration, another is a lower concentration, or one is a higher osmotic pressure, one is a lower pressure. So there is a upper and lower. So like that we can conclude the solution is depends on that isotonic solution and hypotonic, like that. Sometimes the theoretical question asking in the osmotic topic. Okay, thank you to all. If you like this video, you can subscribe and share your friends. Just your command what happened or how is this video, like that. If you see this video, you can comment. Okay, thank you.